Hello, so this is part 2 of the National 5 Chemistry 2022 section 2 paper. So if you're looking for answers to questions 1 to 6, check out my other video. This video is going to cover question 7 and onwards. So if we get started with question 7, a student carried out an investigation to find out how your concentration affects the boiling point of a sodium chloride solution. Before the investigation was carried out, the student prepared 500 centimetres cubed of a sodium chloride solution. This solution had an accurate concentration of 1.5 moles per litre. Calculate the mass in grams of solid sodium chloride required to prepare 500 centimetres cubed of a 1.5 mole per litre solution. So this is obviously a calculation because it says calculate, and if you're unsure where to start a calculation, the best thing to do is to look to see what numbers the question's given you. So the question is telling us a concentration, so we know that a concentration would be the variable C. So if we just pull that out of the question, and then it's telling you to calculate the mass. So mass is M, and because we're trying to calculate that, that's going to be our question mark. And then it gives you a volume here, 500 centimetres cubed. Just remember, always divide volumes by 1,000 to change them into litres. So that'll be 0.5 litres. And the other number here is the concentration again. So this, because we've got C and V, that means we can use the relationship N equals C times V. Because we're trying to find M, that means we then also need to use the MN-GFM relationship too. So you do get these equations at the start of the data booklet. So N equals C times V, N equals M over GFM. You also have the triangle versions that you can use. So for the NCV, the N is on the top, C and V are on the bottom. For NM-GFM, M is on the top and N and GFM are on the bottom. So you don't get given the triangles, but you can remember them if you find them easier to use. So if we go back, we can work out the number of moles, first of all, using the NCV relationship. So N equals C times V. So we just plug the numbers in, that's 1.5 times 0.5. And if we put that into our calculator, 0.75 moles. So that means this number of moles would be the same because we're dealing with the same chemical. And the GFM we can always work out from the data booklet. So the formula is given there. So if we work out the GFM of sodium chloride, so we look up the big table here with all of the elements in alphabetical order. So sodium is here, that's 23. Chlorine is here, 35.5. Then add those together, and that gives you 58.5. So now we know N and GFM, we can use the NM-GFM relationship to work out what M is. So M is equal to, put it down here, M is equal to N times GFM. So in this instance, that'll be 0.75 times 58.5. And if you put all that in your calculator, you will get 43 point, we'll just round it to 8, so it comes out as 875 grams, but you can round it to 43.9 or 43.88. It doesn't matter as long as the rounding is correct. And again, as per my tip before in the previous video, if you watched it, always underline your final answer. It just makes it easier for the marker to find it. So then part 2, name the piece of apparatus that should be used to accurately measure the mass of solid sodium chloride. So you're trying to measure out a solid, which means you would use a balance. So not a scale, not a weight or a weighing instrument, a balance. So that's what you would use to weigh out a solid. If you were looking to weigh out an accurate volume of a solution, you would use a pipette. But a balance is what we use to actually measure the mass of any solids. So then part B, the student heated 3 samples of the 1.5 mole per litre sodium chloride solution until they boiled and measured the temperature each time. The boiling points were 105, 107, 108. Calculate the student's average boiling point for the 1.5 mole per litre sodium chloride solution. So this is just assessing your knowledge to calculate an average. Don't get confused with titration results where you have to only use concordant results. That's not the case here. All the boiling points are relatively close to each other. There's none that are obviously outliers. So an obvious outlier would be if you had 105, 107, and then the last one was like 200. That would be obviously an error. So you are going to calculate the average of all 3 of these. So you would have 105 plus 107 plus 108 divided by the number of numbers, which is 3. So if we add all that up, plus 108. I would always press equals after you've added them before you divide, just to prevent any calculator bod mass issues. So then that comes out as 106.66666, so we'll just round it to 67. And that would be in degrees Celsius. That's you there. So in part 2, the student measured the boiling points for 2 more concentrations of sodium chloride solution. The average boiling point for 0.5 moles per litre was 101.3, and the average boiling point for 1 mole per litre was 104. Present these results and your answer to B part 1 in a table. So to start off the table, you need our headings. So the first heading is always the thing that's been changed by the person doing the experiment. So in this experiment, the thing that they have changed is the concentration of the solution. So our first heading would be concentration. And then the other heading will be whatever is being measured. So they are measuring average boiling point. So that will be our other heading. We also need to make sure that we put in any units for the numbers. So concentration is in moles per litre, so that will be our unit in brackets in that column. And then the average boiling point, the temperature, is being measured in degrees Celsius, so our unit in brackets would be degrees C for that one. So that's our headings. And then now all we need to do is populate the table. So if we fill out the table, so the two concentrations we had 0.5, or there was 3, sorry. So 0.5, 1.0 and 1.5. You do not write the units again next to the number in the table. That's a big no-no because it's already in the heading, so you're just writing in numbers. And then at 0.5, the average temperature was 101.3. At 0.1, it was 104. And at 1.5, that's what we calculated before, it was 106.67. And that's you. So the main thing to remember is the headings and the units in the headings. And don't write the units again. State the type of graph the student should draw to present these results. So we've got a table that's filled with numbers. So if all of your data has numbers, it's a line graph. If you had words in the first column, then that would be a bar graph. So all numbers is a line graph. If there's some words in your data, then it would be a bar graph. So in part D, the student's aim was to find out how the concentration of a sodium chloride solution affects its boiling point. Suggest a conclusion for the experiment based on the student's results. So if we look at the table, we can see that as the concentration increases, the boiling point, average boiling point, also increases. So that would be our conclusion. So as the concentration increases, the average boiling point increases. With these questions that are forming conclusions, you need to make sure that you get the variables the correct way around in the statement. So a common thing some people do is they'll say that as the average boiling point increases, the concentration increases. But you have to remember that boiling point doesn't affect concentration. Concentration affects boiling point. So the cause and effect have to be the correct way around. So whatever's causing the change goes first. So changing concentration causes the average boiling point to change. So the concentration would have to be mentioned first. So then question 8, a student carried out 4 reactions with dilute acid A as shown in the diagram. Name dilute acid A. So if we look at what's actually been formed, so we're forming things like copper sulfate, barium sulfate, sodium sulfate, water, carbon dioxide, magnesium sulfate, gas. So the thing that's common to all 4 of the things that are formed is the sulfate. And hopefully you know that the name ending of a salt, so copper sulfate, barium sulfate, magnesium sulfate, sodium sulfate, these are all salts, and the end of the salt name always comes from the acid. So if your salt name ends in sulfate, you must have used sulfuric acid. If the salt was to name in nitrate, it would be nitric acid. If it ended in carbonate, it would be carbonic acid. If it ends in chloride, it's hydrochloric acid. So if you're not clued up on your salt name endings, then have a look at that in your class notes and maybe put them on a flashcard or something. So then for B, you're asked to name gas B. So in this particular reaction here, you're reacting the acid with magnesium. So when you react a metal, which is what magnesium is, with anything really, you always end up making hydrogen gas. So anytime you're reacting a metal, if you're asked what gas is produced, it's going to be hydrogen. So gas B would be hydrogen gas. That's from Unit 3, Metals, Reactions of Metals topic. So you can have a look back over that if you feel you need to. And then C, sodium carbonate is added to dilute acid A until the reaction is finished. Other than measuring the pH, suggest how the student would know when to stop adding sodium carbonate. So when you're reacting the acid with the sodium carbonate, you're making carbon dioxide. So anytime you use a carbonate in a reaction, it will produce carbon dioxide gas, which means that you know the reaction's finished when it stops fizzing or bubbling. So that's why it's quite useful for when you're carrying out neutralisation reactions, because you can actually see when the substance has been neutralised, because the bubbles will stop. So it stops fizzing or bubbling. You can use either word really. So then D, in all of these reactions as a salt is produced, state which of these salts would be produced as a precipitate. You may wish to use the data booklet to help you. So if it's a precipitate, it means it's going to be a solid, which means it's going to be insoluble. So when it says to use your data booklet to help you, we want to look at the solubilities table. So that's the big table with all the I's, the VS's, the S's in it. So we're looking for something that has an I, because that means it's insoluble, and so it would precipitate out and form a solid. So if we go back and remind ourselves what all the salts were. So if we look up copper sulfate first, so we would find copper and then go along to where it falls in line with sulfate. So that's very soluble, so that's not going to be our precipitate. We look for magnesium sulfate next. So down to magnesium, along to sulfate. Again, that's very soluble, so that's not going to be our precipitate. Barium sulfate. We go to barium, along to sulfate. That is insoluble, which means that will be our precipitate. So barium sulfate would be produced as the precipitate. As they say, if you're not part of the solution, you're part of the precipitate. Anyway, moving on. So, unlike other reactions in the diagram, the reaction between magnesium and dilute acid cannot be classed as a neutralisation reaction. State what is meant by a neutralisation reaction. So the definition of a neutralisation reaction that we're looking for here is where you state that it's a reaction between an acid and a base to produce water. And a salt. Okay, so a neutralisation reaction is where you react an acid with a base and you produce salt and water. So again, that's a good one to put on a flashcard where you can have neutralisation on one side and then the actual definition on the other. You can do that for all different types of reactions that you cover in National 5 as well. And any other words that you need to know the definitions of, like isotope, isomer, ion, things like that. They're all good things to make flashcards with. So, number 9, xenon is an element found in group 0 of the periodic table. A number of isotopes of xenon exist. State what is meant by the term isotope. I swear I didn't know this question was coming up when I just said to make a flashcard of this. But again, there's another definition that they want you to say for this. So there are a few ways you can phrase it, but the way I like to phrase it is that they are atoms of the same element with a different mass. Okay, so atoms of the same element with a different mass. So that's what's meant by isotope. This definition is quite often mixed up with isomers, which are molecules with the same structure, same molecular formula but different structure. Isomers has an M in it, and M is what molecules start with, so that's one way of trying to remember which one's which. So isomers is for molecules, isotopes is for atoms. So part B, the elements in group 0 are known as the noble gases and are all very unreactive. Explain why the noble gases are unreactive. So that's because they have stable electron arrangements. So elements only react to try and get stable electron arrangements. So if they already have a stable arrangement, they won't react. So as they have stable electron arrangements. Remember, a stable electron arrangement is where they've got a full outer shell of electrons. So then part C, under certain conditions, xenon can form compounds. Xenon hexafluoride is made by reacting xenon difluoride with fluorine using nickel 2 fluoride as a catalyst. Write a chemical equation using symbols and formulae to show the reaction. There is no need to balance this equation. So it tells us in the question what the reactants are. So if I highlight the reactants in green, so you're reacting xenon difluoride with fluorine and you're using nickel fluoride as a catalyst. So remember, catalysts don't go in the equation. They help the reaction go faster, but they don't take part in the reaction, so they're not going to go in our chemical equation. And then our product, the thing we're making, is xenon hexafluoride. So they've given us the formula for xenon hexafluoride, but we need to work out what it is for the other ones. So xenon difluoride, because there's a di there, that tells you there's 2 fluorines. So that'd be XeF2, because that's the symbols for the 2 elements. And you're reacting it with fluorine. Remember, fluorine is one of the 7 diatomic elements, so that has to be F2. And then we're producing the xenon hexafluoride, which is XeF6. And you don't need to balance it, you don't need to show state symbols either. So that's your final answer. So part 2, xenon hexafluoride is a solid at room temperature with a melting point of 49 degrees. State the term used to describe the structure of xenon hexafluoride. So if something is a solid at room temperature, but it has a very low melting point, so by very low I mean like below 1000, then it would either be potentially a metal or a covalent molecule. Okay, ionic substances and covalent networks generally have melting points above 1,000. Okay, so we're looking for basically what types of elements are in it. That'll tell us what the bonding is. So xenon is a non-metal. Fluorine is also a non-metal. If you're not sure, you can check on the data booklet. Remember, this black staircase separates the metals and non-metals. So xenon's on this side, the side that's non-metals. Fluorine is also on the right-hand side of the staircase, meaning it's also a non-metal. So if you have two non-metals, it's going to be a covalent substance, and if it's a covalent substance with a low melting point, then it would be a covalent molecule. So the structure would be covalent molecular. I can't spell. Sorry, let me fix that. Okay, so all non-metals and low melting point covalent molecular. All non-metals and a melting point above 1,000 would be the covalent network. So that's how you can tell the difference. I do have a video on summarising the properties of bonding for National 5. If you're struggling with that, you can have a look at that as well. So part 3, when making a sample of xenon hexafluoride, 35 grams of nickel 2 fluoride is required to catalyse the reaction. Suggest what mass of nickel 2 fluoride should be present at the end. So remember, catalysts don't get used up in the reaction, so if you start off with 35 grams, you're going to finish off with 35 grams. Easy as that. Calculate the cost in pounds of purchasing the required mass of nickel 2 fluoride if nickel 2 fluoride can only be bought as a 10 gram tub for £69.40. So you can only buy it in 10 grams, which means that we will need 4 tubs. So we'll need 40 grams. We can't get 35 grams because that's not a multiple of 10. So we need 4 10 gram tubs to give us 40 grams. Oops. So we need to times the price of 1 tub by 4. So if we do that, 4 times 69.4, that's £277.60. So they will have some catalyst left over, but they can always use that in the next lot of the reaction. But you can only buy it in 10 grams, so you have to get 40 grams. So question 10. Alcohols are a homologous series used for a variety of purposes in everyday life. State what's meant by the term homologous series. So another textbook definition, one that can be put on a flashcard. Homologous series is a family or a group of molecules, you can call it either or. Family of molecules with the same general formula and similar chemical properties. Okay, so molecules with the same general formula and similar chemical properties. That's one that people often get mixed up with the definition of isomers as well, because there's quite a lot of the same words in it, so just be careful. And again, if you are struggling, get some flashcards made up and you can get other people at home to test you, or your friends at break time, lunchtime. Depends how sad you are. So B, alcohols can be classified depending on how many hydrogen atoms are attached to the carbon atom bonded to the functional group. This carbon atom circled in the examples shown. So you've got where there's 2 hydrogens attached, and that's showing an example of what it looks like. So this is the carbon they're talking to, the one that's attached to the functional group. That would be a primary. Where there's only 1 hydrogen attached to that carbon, that's a secondary, and where there's none, that's a tertiary. But the first question is asking to name the functional group present in all alcohols. So this is the functional group here, the OH group. Hopefully you remember that's called a hydroxyl. Okay, not hydroxide, that's the ion that's in acids and alkalis. So don't get those confused. Okay, it's a hydroxyl, not a hydroxide. So then part 2, this is about problem solving. So you've got the structure for 3-methylbutan-2-ol shown. Identify the alcohol classification of 3-methylbutan-2-ol. So this is where we need to use this table of information we've been given. So this is brand new information to us, so don't panic. It just might take a little bit of thinking, but if we look at what this information is telling us, we're looking how many hydrogens are attached to the carbon the functional group's on. So this is the carbon we're talking about here, because here's our hydroxyl group. So this carbon, if we look at it, it's got 1 hydrogen attached to it. Everything else is either a carbon or oxygen. So we're looking for where there's 1 hydrogen attached to the carbon with the functional group, and that would be classified as a secondary alcohol. So that's our answer, secondary. That's it. So then draw an isomer of 3-methylbutan-2-ol which has a different alcohol classification. So normally when we are making isomers, we would just take a branch and stick it on the end. However, this one's a bit more difficult because it needs to be a different alcohol classification. So in order to do that, we need to move the hydroxyl group. Okay, so rather than moving the branch, we're going to move the hydroxyl group. So we either need to move, to get a primary or a tertiary, which is a different classification, we either need to move the hydroxyl group to the end carbon, where there'll be 2 hydrogens on the carbon, or we need to move it to the same carbon as the branch, so that it would be a tertiary. So we'll just move it to where the branch is, that's probably easier. So we've got our chain of 4, the branch here, and then we're going to put our hydroxyl group on that carbon now, and then that makes it a tertiary alcohol. And the rest of it will just be filled in with hydrogens. And that's it. You could also draw the primary, which would be 1, 2, 3, 4. And we just can put the hydroxyl on the end. So you could have done that instead. Either of those is fine. Yeah, it's quite a tricky one for an isomer drawing question, to be honest. So then question 11, the screaming jelly baby is a popular chemistry demonstration where the sugars in a jelly baby react with oxygen. In the demonstration, potassium chloride is first heated in a boiling tube until it decomposes, producing oxygen gas. Describe how you could test for the presence of oxygen. So you need to know 3 gas tests. You need to know the test for hydrogen, you need to know the test for oxygen, you need to know the test for carbon dioxide. So the test for oxygen is that it relights a glowing splint. Okay, just in case you're not sure of the other ones. For carbon dioxide, that turns lime water cloudy. And hydrogen burns with a pop. Okay, so again, these are things you can put on flashcards. Then part 2, write the formula for potassium chlorate, showing the charge on both ions. So this is asking for an ionic formula. So we've got potassium and chlorate. So remember, anything that ends in 8, you can find on page 8 of the data booklet. So we'll go and look at the charge of chlorate first. So chlorate is not actually on this table, which makes this question much more difficult. So we then will have to look at the main group element. So potassium has a fixed charge, so it can only ever have 1 charge as an ion. So if we go and look at the periodic table, or the electron arrangement page, so potassium's here in group 1. Anything in group 1 ends up with just a single positive charge. Group 2 end up with 2+, group 3 end up with 3+, group 4 don't really form ions. And then once you get across to group 5, the ions become 3 negative, then 2 negative, then a single negative, and then again group 0 don't form ions. So if you struggle to remember the charges of ions for the main group elements, just put these this at the top of your data booklet on this electron arrangement page, and it can help you remember it for the exam. So the potassium is a positive, so that's going to be a plus there. And the chlorate then, because we're not told in the data booklet what charge it is, we just have to go off the fact that it must cancel it out. So to cancel out a single positive charge, you must need a single negative charge. Okay? So again, quite a tricky ionic formula question, that one. So part B, the jelly baby is then added to the reaction mixture. The sugars in the jelly baby undergo an exothermic reaction with oxygen. State what's meant by the term exothermic. So that's a reaction that releases heat energy. Again, another definition you need to know. The opposite of exothermic is endothermic, which is one that consumes heat energy. You can also put into the surroundings, but it's not really required. Here's me writing in the do not write margin again. Standard. So part 2, during the demonstration, brightly coloured flames are produced. Suggest why the flames are lilac colours. So if it's asking about flame colours, we can use this page in the table here. So lilac occurs because you've got potassium present. So there's potassium in the potassium chlorate, so that's going to give the lilac flame colours. So as there is potassium in potassium chlorate. Seems a bit obvious, but that's what they're asking. So then part C, calculation from equation. So calculate the mass in grams of oxygen required to completely react with 2.25 grams of glucose. And it gives you the formula for glucose. So we're looking for the amount of oxygen and to react completely with the glucose. So then we're given a mass of glucose. So that's going to be the two chemicals we're using for this calculation. So I'm going to write their formulas again. So that's the glucose, the oxygen, and then we're going to put the mole ratio in the middle. So there's no number in front of here. And there's a 6 in front of here, so that'd be a 1:6 ratio. And we're dealing with masses, so we would be using the NM-GFM relationship. There is another way of doing and laying out these calculations, but I'm not going to go into it. So if you do lay out a different way, it's fine. You can just check to see if your final answer comes out the same. So we've got a mass of glucose, so we can put that here. You'll never be given the number of moles in these calculations usually, so if you end up with a number next to N before you've calculated anything, you probably made a slight mistake. And then if we work out the GFMs, so for oxygen, that would just be 2 times 16, because each oxygen is 16, so that'd be 32. Ignore the 6 here, don't times it by 6. And then for the glucose, we need 6 times 12 for the carbons, plus 12 times 1 for the hydrogens, plus 6 times 16 for the oxygens. So that'd be 180 grams. So you should be able to see now that the only place you can start is by calculating the moles of glucose. So N is equal to M over GFM. So if we do that, 2.25 over 180, that gives us 0.0125 moles. So now to go across, we use the mole ratio. So we're going from 1 to 6, which means we times by 6 in this case. So we times that number of moles by 6. That gives us 0.075. And now we have N and GFM, we can work out M. So M is N times GFM. So 0.075 times 32. And that gives us 2.4. So you need 2.4 grams of oxygen. So then question 12. Covalent radius is measurement used to indicate the size of an atom. The diagram below shows the covalent radius for elements in groups 1 to 7 of the periodic table. Describe the trend in covalent radius going from sodium to chlorine. So as you go from sodium to chlorine, this number is decreasing. So you would just say the trend is decreasing from sodium to chlorine. So again, some more problem solving. describe the general trend in covalent radius going down a group in the periodic table. So it's saying general, which means that there might be slight fluctuations, but you're just looking at like overall what sort of patterns do you see. So if we just pick this first group here, so as you go down the group, the covalent radius is increasing. Same thing for this one, same thing for this one. So going down a group, the covalent radius increases. And then part 3, predict a value in picometers for the covalent radius of strontium. So using the patterns we've just observed, it's most likely going to be bigger than 174, but it'll be smaller than 215, so it needs to fit in between those two somewhere. So if we just pick any number between those two, so I'm just going to go for 201, but you can pick any number between 174 and 215 because those numbers would be fitting the pattern. So 12b, the covalent radius is defined as being half the distance between two bonded nuclei. Calculate the distance in picometers between the nuclei in bromine. So if we go back to this table, it's telling us the covalent radius of bromine is 117. So that means this is 117. So if we want the distance between the two nuclei, we just have to times that by 2. So that would give us 234. And you don't need to put the units because they're in the question, but you can always copy them anyway as good practice. So then C, the radius of the sodium ion Na+ is smaller than radius of the sodium atom. Write the electron arrangement for the sodium ion Na+. You may wish to use the data booklet to help you. So electron arrangements mean electron arrangement page. So sodium is normally 281. If it's sodium positive, that means it's lost one electron. Because remember, although it's plus, it means a loss of a negative electron. So that means the electron arrangement becomes 2,8. Okay, and then suggest why the radius of the sodium ion is smaller than the radius of sodium atom. So if we go back and look at the sodium atom, now the radius is to do with the size of the atom, so how sort of wide it is, if you like. So the arrangement for sodium, if you remember the structure of the atom, it's got the electron shells and they are like layers, kind of like an onion. So the sodium ion is 2,8, so that's got 2 electron shells occupied. The sodium atom is 281, so that's 3 electron shells occupied. So the atom is bigger because it's got an extra shell of electrons. Or you can say that the ion's smaller because it has one less electron shell. Because the question is asking about the ion. So the ion has one less electron shell. So it's like peeling a layer off an onion, which makes it smaller. And then lastly, this open-ended question. So it's all about redox reactions. So redox reactions involve both an oxidation and a reduction. Using your knowledge of chemistry, comment on the chemistry of redox reactions. So there's quite a lot you could really talk about here because it is very vague. So it leaves it open to a lot of things. So obviously you could start by giving the definition of oxidation reduction. So oxidation is loss of electrons, reduction is gain of electrons. I'm just going to bullet point ideas here. Obviously in the exam you would write them out fully. So you could start off by explaining what oxidation reduction is. You could then give examples from the data booklet from the electrochemical series. You can give some ion electron half equations. So remember, they are reduction reactions as they are written from left to right. So if you want an oxidation, you just have to write it backwards. So then you could also then show how you combine the reactions. So show ion, electron, half equations. Combine half equations for overall redox reaction. So that's where you get the electrons to cancel out. So you might need to multiply them, whatever, to get them to cancel out. Redox reactions are generally used in batteries. So you could, used to generate a source of electricity, because it allows free moving electrons. And then the easiest thing to draw would probably be a wee cell. So where you have your two metal electrodes with your either the voltmeter or the ammeter in between. And then this is always an electrolyte solution. You could explain that an electrolyte is a solution that is an ionic solution that allows conductivity. So that completes the circuit. Other things that you can add is that in the cell, so if say this was copper and this was magnesium, you'd explain that the electrons flow from the metal highest in the electrochemical series to the lowest. So in this case it would go from magnesium to copper, and that they would flow through the wires. So electrons flow from Mg to Cu through the wires. Again, you could explain if you change the metals, that can change the voltage. So the further apart the metals are, the bigger the voltage. The closer they are, the lower the voltage. So you could give, again, specific examples for that. So you could say if you swap the magnesium for tin, the voltage would decrease. Okay, and then you could also kind of mention titrations here. So you don't really do redox titrations in National 5. You do acid-base ones. However, you can use redox reactions in titrations to calculate concentrations of substances. So that could be something else you could potentially add in. But again, you wouldn't need to talk about all of these things that I've mentioned. These are just ideas. But fully explaining as many things as you possibly can helps you get from 2 marks to 3 marks. But yeah, this parts here would definitely be what they would be looking for you to be discussing in some respect. And yeah, writing out fully, drawing diagrams, writing equations out, all the things like that can help bump your mark from a 2 up to a 3 if you've got enough statements down. Excellent. Well, that brings us to the end of that paper. I have to say it was actually quite a tricky paper. I'm a bit surprised, slightly disappointed as well after 2 years of COVID and no exams, but there we go. That's just the SQA and life for you. So maybe the 2023 paper will be a bit nicer. But yes, feel free to leave a comment, like, subscribe, check out some of my other videos, and yeah, thanks again for watching.